Good morning. This is our second day. I hope some of you had fun yesterday. I mean, as far as I'm concerned, I was very busy and tired, so I slept. That was fun for me. Well, I'm going to talk today about the biomechanics of the knee joint in deep flexion, and basically I'm going to present a summary of the work that we have done over the years, and what did we learn from it, and what are the consequences, implications on total knee replacements. Let me start first by showing you a picture of our beautiful campus at the University of Toledo. This is our engineering complex. And we have here something called Center of Commercialization, where we try to move bench work to commercialization. And we have been doing that for some time in our College of Engineering. When I was young, I was fascinated with the $6 million man. I don't know if anybody of you remember it or not, but basically it is basically developed by a guy from the FDA at that time, and it is my understanding that it is now in the National Museum as the Smithsonian. Now, as far as Zurich is concerned, I was interested for a long time over the knee joint. And as mentioned yesterday, and we have a model here, from one of my colleagues from Turkey, right? And it is really a complex joint. And when people talk about the knee joint, that could be misleading, because really at the knee joint there are at least two joints. Because a joint is articulation of one surface over another. So what we have here, we have the tibiofemoral joint, and we have the patellofemoral joint. So when we talk about the knee joint, we need to be a bit more specific. What are we talking about? Now, if you talk about reasons for knee replacements, it is due to degenerative arthritis. And that could be osteoarthritis or rheumatoid arthritis or traumatic arthritis. And this is one of the slides showing the damage that occur at the articular cartilage. Now, the damage causes a lot of pain. And not only pain, it causes also decreased mobility. Now, in the United States, there are about over 40 million people affected by arthritis. There is about 10 million in the United Kingdom, and there is tens of millions more worldwide. So that is a real health problem. And if we are talking about quality of life, and that in our generation, people tend to live longer than previous generation, then that becomes a real issue. Now, there is a study that has been done in 2007, and it showed that demand for total knee replacement is projected to grow by 673%, from 450,000 in 2005 to 3.5 million in 2030. That is a projection by a study that was done, I believe, and published in JBJS, Journal of Bone and Joint Surgery. Now, the question with total knee replacements, and it has been there for a long time, means basically people are satisfied with it because it produced normal knee flexion angle up to 125 degrees. The question is what we call deep knee flexion, which is what about past 125 degrees? And why this is important? Why this is important? Well, high flexion activities really go to 165 degrees. And if you are looking at the non-Western cultures, there are social and religious activities in the Middle East, in the Far East, where praying, resting, eating on the floor, all of this requires deep knee flexion. If we look at the Western culture, there is leisure activities that people started to appreciate, especially elderly, because basically when people retire, one of the things they enjoy doing is gardening. And for younger generation, there is recreational sports. And these are some pictures of these activities. So this tells me that people function in deep knee flexion. That is why it is important. Traditional knee replacement rarely achieve more than 115 degrees of flexion. Changes have been made to the design of TQ, total knee replacement. And I'm not going to go of different publications, but this is a patent from Japan, and it shows, and the patent claims that it can produce deep knee flexion. Another work, another patent, which is recent, November 2013, and this is prosthesis to facilitate deep knee flexion. So over the years, there have been claims that, yes, it works. And from this, we have learned new designs. What are the new designs that allow deep knee flexion? And there is a common agreement that extending the posterior condyles and reduction in the condyle area and having a tibial spine and cam mechanism where the contact point move downward in the cam, creating a large jump distance, is so-called jump height, and that produce increased reduction in subluxation. So these are some of the common design that help in assisting in deep knee flexion. And these are summarized by Chenoy in 2013 on orthopedics and trauma. As far as tibia is concerned, the anterior margin of the tibial articular component should be recessed to reduce impingement of the extensor mechanism. These are some of the common change in the designs in total knee replacement to allow deep knee flexion. However, in 2009, Murphy et al. In International Orthopedics conducted a systematic review of published studies on high total knee replacement. And he concluded that they failed to show improved range of motion. That is in 2009. He may be here, so I may need to short. I need to check if he is a speaker.
Professor Yongwang? Excuse me? Professor Yongwang? Oh, no?
No, good.
Thank you.
Also, Hamilton et al. In orthopedics in 2011, in more recent study, have shown that a comparison between standard posteriorized stabilized TQR and a high flexion posterior stabilized TQR. So these are two specific designs where one is for specific high flexion. And he found that there is no significant difference in clinical flexion or range of motion. So these are two clinical studies that have shown there is no significant improvement in range of motion. Well, what is the implication of this? Is that patients prefer to live with pain of arthritis if ability to return to daily living activity is not assured. And I have seen that personally when I have worked in Saudi Arabia, and I have seen that also in Egypt, in the Middle East, where people, if you don't ensure for them that they are going to return to praying or sitting cross-legged, they will refuse to do a total knee replacement. So what are the factors that influence the development of a new TQR? On one side of the scale are the different surgical procedures, method of fixations, choice of materials. On the other side of the scale is modeling the function of the human knee joint. Because if you don't know how something functions, how you are going to duplicate it. So what I'm going to talk about is I'm going to present to you some of the studies that have been done by my group over the years and some of the ongoing studies. And early studies are three of them: a radiographic assessment study, a CT scan study, and a two-dimensional modeling of the deep squat. The first study, really, that is where I started working in that area, this particular deep knee flexion, was in 95 to 97 when I did my sabbatical in Saudi Arabia. And we published a paper, kinematic of the knee joint in deep knee flexion, a radiographic assessment. And fortunately, thanks to God, this paper has been cited so far 89 times in many citations. And you can check it, Google it on the web. And the reason was, it was the first study that provided, in my opinion, a subjective, not yet quantitative, a subjective method of telling us what is going on in deep knee flexion. Basically, and I was one of the guinea pigs, and basically I took an X-ray, an AP view, and a sagittal view. Well, the AP views were interesting because they told us, they showed me here that these are subject 2, subject 3, subject 4, 5, and if you look at the femoral and tibial axis, all of them makes an angle, except this one where they were aligned. And we asked ourselves, why is that? Went back and forward, and basically the reason, and until now even, in subject 1, the ankle was underneath the buttocks. While subject 2, 3, 4, and 5, the ankles were lateral to the buttocks. As you sit and kneel and pray, sit and kneel, where do you put your ankle? Is it underneath the buttocks, or some people put it lateral, some people put it medial? And this will have definitely, but we have not studied yet, what is the effect of that at the knee joint? Does it produce a valgus? Does it produce a varus? Abduction, adduction? But so this was one of the first conclusions. The second important conclusion is that we found in deep knee flexion that the patella clears the femoral groove. And it is very flexed with respect to the tibia. If you go, as we know, that the tibial flexion, patella flexion lag tibial flexion. So as you go from 120 degree knee flexion, your patella flexion is about 70 degrees. There is a lag. However, from 110 degrees to 150 degrees, there is almost one-to-one increase between patella flexion and tibial flexion. So the patella is highly flexed in deep knee flexion. And it is in contact only with the femoral condyle because it clears the femoral groove. If we looked in the study at the tibiofemoral contact, it appears that the contact occurs on the femur on the most proximal point of the posterior condyles. And this is an enlargement where the contact is very posterior, very proximal on the condyles, and very posterior on the tibia. So that was an important conclusion. But as I said, it was subjective because it was just X-rays. Then, when I returned from Saudi Arabia, I did a CT scan study where this is person, I believe that was me, I don't remember really, and we just did a CT scan of the knee joint while kneeling. And now we're documenting with a CT scan data that the patella clears the femoral groove completely in deep knee flexion. and it is in contact with the femoral condyles. So that is one of the very first takeaway message that I like people to have at the end of my presentation. What are the takeaway message? One of them is that over the different studies, you're going to find that we prove that, among other people, that the patella clears the femoral groove completely in deep reflection. Now, we had our slices from CT scan, so we used Scion image software, which is an NIH software, to create a reconstruction of the tibia and femur. And then there was a computer-aided design, finite element software called IDEAS, where we imported this slice too. And so using Scion software and IDEAS, we were able to reconstruct the knee joint when kneeling and try to study it more quantitatively. The most important conclusion that we found that there is an asymmetric position. In deep knee flexion, the knee is highly asymmetric. This is the reconstruction. So what we did, we say, okay, what if we take slice on the medial side and a slice on the lateral side? And let us see what the contact appears to be. Well, we found that on the medial contact, there is an impingement against the posterior femoral cortex. And it appears that there is a contact. There is a contact on the tibial eminence. And these results were in agreement with Yildirim et al. Results, and I refer to Yildirim a lot. I don't know if some of you know him or not. He was working with Professor Walker at New York Joint Hospital. And that is another takeaway message, that in deep knee flexion, on the medial side, there is an impingement against the posterior femoral cortex. And the contact is on the tibial eminence. Some people refer to that as tibial, there is a lift-off. Some people refer to that as a lift-off in deep knee flexion. In the lateral contact, the contact were very posterior on the tibia and as extreme posterior surfaces of semihemur. And this was also in agreement with Yildirim results. And this is the reconstruction of the knee joint at 160-degree flexion, and this is the posterior cruciate ligament. I'm not going to go to that, but we modeled the ACL, we modeled the PCL, and we modeled the collaterals in order to assess, are they tense or not? And our assessment is tense or not. Are they elongating? What is the lens pattern? But the most important thing, it is again documenting that there is an asymmetric contact. The next step, we say, okay, let us now start doing some modeling, not using ideas, not using software, but doing some kinematic modeling. And kinematic modeling, it can be three-dimensional or two-dimensional. So we started doing by a two-dimensional modeling of the tip squat. And in order to do that, I need input, and the input was the geometry of the joint and the joint loads. And we used force plates and markers to determine the position of the joint and the reaction load. And the model, and I think I'm almost sure about that even this is the only published model that considered the thigh and calf contact. When you go in deep knee flexion, you can, if you bend your knees and sit kneeling, you are going to have a thigh and calf contact. What is the effect of that? There is and how to model that? And modeling that is not something simple, because you have a large area of contact on the side. and the stress distribution is not uniform. So what we did, we say, okay, and the reason we incorporated that is that when we started doing the two-dimensional model, and we used here two joints, simplified joint for the patella was just a plane, and we had a co-contraction of the quad and the hamstring, and we had wrapping around the femur. Now, when we tried to model that without the two-dimensional model, without the thigh and calf contact, we did not get convergence in our results for whatever reason. So we started asking ourselves questions, and then we said, let us introduce the thigh and calf contact. And basically, we introduced it as a single force acting perpendicular to that bisector line between the two axes of the femur and the tibia. And the unknown in the model was the magnitude of the force and the location of the contact force. And we modeled the different ligaments having different bundles, like the ACL has two bundles, the PCL has two bundles, and so forth. And the model input was flexion angle, joint loads, which were obtained by the force plates, and the geometry of articular surfaces. And the output was simply the contact characteristics, which is where contact occurs, what is the value of the contact force, and so forth. And these are the profiles that we used. We used a tens order polynomial profile between the femur and the tibia. And here is our results. We started to see that going from 130 degree, 140, 147, and 156 degrees, that in high flexion angle, that is the two model prediction, besides their plane, there is a impingement on the femoral cortex, which people refer to that as a liftoff. So this is the second study that we did that told us quantitatively that there is an impingement on the femoral cortex in deep knee flexion. Also, one of the findings of this model is that we found that the angle that the patellar tendon makes with the longitudinal axis of the tibia increases with deep knee flexion. And that is a kind of consistent with the design changes that made to make a assessment in the anterior portion of the tibial insert to allow for this. And these results, modeling results, these our modeling results, were verified experimentally by a group in Japan, Komatsu et al. In 2008, where they have shown that this is the patellar tendon angle in deep knee flexion, and you can see how the angle increases in deep knee flexion. So these findings were verified experimentally by another group in Japan. Our ongoing studies regarding the contact characteristics are two studies going hand in hand. Experimental studies and finite element studies. Both studies are in vitro, meaning that we are using cadavers, and the data obtained from the experimental studies is used in the finite element model. And we determine the contact characteristics in experimental study two methods, one using a sensor and one indirect method. I will explain those briefly. So what we have, this is our experimental setup, and it uses servo motors to simulate quadriceps and hamstring loading. So we try to produce co-contraction. And we had something called a hip slider where these motors were attached to. And two servo motors with gear reducers are used to simulate hamstring and quad flexion. And what is, means this experimental setup means the people at, I believe he did his PhD at Purdue, and then he moved to University, where they have a similar experimental setup with much more sophistication. But what is the advantage of this setup compared to any experimental setup I am aware of? You can have the experiment conducted vertically, and that simulates deep reflection, it simulates squatting. Or you can have the setup turned around and the experimental conducted horizontally, and that simulates rowing motion. So what you have here in this, it allows you to have different simulation. The ankle was controlled using an XY table, and what we have here to measure joint motion is, is what we used a three-space fast-track system. And what is a three-space fast-track system? Basically, it is an electromagnetic device where you have a sensor, and that is a sensor mounted on one bone, and you have two sources, one source mounted on one bone, and two sensors mounted on the patella and sensor mounted on the other bone. So the source, basically the output of this device, what it gives me? It gives me, there is a system of axes here, there is a system of axes, and there is a system of axes, three-dimensional. So there is a three-dimensional source system, there is a three-dimensional sensor system, there is a three-dimensional sensor system. That system of axis has an origin, right? So there is orientation and there is origin. And the output of this device gives me the position of this axis in each sensor with respect to the source at different positions. So the three-dimensional system, which is a fast track, and it has been used by many, many, many investigators. It's a very well-known system. And it has another newer version, fast track, another newer version called flock of birds. And basically, these allow me to measure, again, the relative position and orientation of one moving body with respect to a fixed body. And here is, I don't know if this will work or not. Now, I hope it does. I don't have a mouse. So let me escape and see if it works or not. I will do it again. Let me. Go back. Now, it is working, but now let me do a slideshow. We don't know if it works or not, a slideshow or not. From current slide. And you can see here the system moving from deep reflection, in this case, to full extension, using the input from the controlled by quadriceps and hamstring. Also, we had here what happened. So what are some of the results we got from, from these experiments? As you know, we know that what we call the screw-home mechanism is that as the knee flexion increases, the tibial go in internal rotation, right? But what we found is that during the last 30 degrees of knee flexion, from 120 to 150, the tibial start going back into external rotation. And we had this finding for some time with no collaboration or no verification or no documentation from any other investigator. Until recently, in 2014, again, a group from Japan, Wang et al., conducted a similar study, and he reported that the knee go in internal rotation until about 110 degrees, 120 degrees, then it start going into external rotation. So this basically he is in agreement with our data. That is important to know, because always we think as we flex the knee, the goes in internal rotation. But that is not in all the range. In deep knee flexion, it starts going back into external rotation. And the second method, we wanted to find the location of the contact area. And for this, we used the TEC scan sensor, and we used indirect method. Let me talk about the indirect method first. The indirect method basically is that you have the position of the patella and the femur with respect to the tibia. You have that. This is called motion data. After we are done all testing, what we do is that we dissect the specimen. And we digitize the articular surface. Dissect the specimen, we digitize the articular surface. So now I have the exact point of the articular surface. I combine this with my motion data, and I get the position of one body with respect to the other. If there is a penetration at a given point, this cannot happen. So this means that there is a contact. This is the indirect method. So we have here the TEC scan sensor and the indirect method. Now, the TEC scan sensor is shown in this figure, and basically it allows me to determine if there is contact or not. And this is a picture of the TEC scan sensor inserted in the patellofemoral joint during testing. And what we found is that the patellofemoral contact area decreases in deep knee flexion in the last 30 degrees. Patellofemoral contact area decreases in deep knee flexion in the last 30 degrees. This was also reported by another study from Japan. Most of the studies I'm referring to are from Japan. They are doing a lot of studies in deep knee flexion. Nakagawa et al. Have shown and reported in his study in 2000 that the total contact area stay almost constant, and then it reduces in deep knee flexion. The total contact area reduces in deep knee flexion. Patellofemoral contact area. This is an important finding. Then what we did is that we want to do our finite element model. So in order to do that, I need geometry. So we used a CT to collect CT data. And basically, we put the specimen in a CT to get CT data from the specimen. The cadaver specimen, after dissection, remember, the source and the sensors are still mounted on them. So we got a DICOM images, and we used a software called the 3D Doctor. And the 3D Doctor allowed us to do a reconstruction of the DICOM images and save them as STL file. And then we use SolidWorks to make the transformations between the different coordinate systems. And you can see here the bone and the source mounted on it, the bone and the sensor mounted on it, the bone and the sensor mounted on it. And using SolidWorks, we are able to do a 3D reconstruction of the joint at different flexion angles. We do a CT scan only in one position, but we have the reconstructions using transformation. We can do the reconstruction at different flexion angles. Then we used a NetGen meshing software to do a volumetric mesh, three-dimensional volumetric mesh of the femur, the tibia, and the patella. And then we imported this into Abacus and assembled them together. And we were interested in studying 4 positions, 90, 120, 135, and 158. And as I told you, this is an ongoing work. So to begin, we had added cartilage layer. We have cartilage layer added. And the patella cartilage layer, femoral cartilage layer, medial and tibial plateau cartilage layer. And all the structures were assumed to be linear, elastic, and isotropic materials. And that is an assumption. We used the connector elements to insert the ligamental structures. And we did that based on the anatomical data that are published about where the ligamental structure should be. And there are several ways to address the contact in abacus, and we use the penalty method to define the contact between the sliding surface, and we had a very low coefficient of friction of 0.005, because as we know, there is a synovial joint, and there is friction, but very low friction. And we use a friction formulation was defined with isotropic friction directionally. You know, some of you have used abacus here and may be familiar with this identification. And using abacus, we were able to do the study the interacting surface at different flexion angles. In loading, while our experimental data provide us loading for quadriceps and hamstring, and again, as first step, we used only a quadriceps load of 400 Newton. Here are the results. The patellofemoral contact at 90, 120, 135, and 158. These data provide us a lot of insight in the location of the contact, and it is in agreement with the result by Peter Walker, Professor Peter Walker, and Yildirim. And here is the findings. On the femur, at large flexion angle, the contact is above the intercondylar notch. You can see that. And there is a medial contact adjacent to the notch. On the patella, the contact is over the superior half of the patella. More important, there is a medial contact on the odd facet. So in deep knee flexion, you have a contact on the odd facet. And here are a comparison, one-to-one, with two studies, our results and Pete Walker results, Yildirim et al. If you look at this, and what they did here is something which, again, I call the indirect method. And basically what they have here are three colors: light blue, solid blue, and green. And we want to focus on the solid blue. Why is that? Because solid blue is telling me, according to their results, that there is a 0 to 1 millimeter separation. Light blue and green, 2 to 3 millimeter separation. So the solid blue tells me that there is a contact, because the surfaces are very close to each other, according to them. And if you look now at the results, here is the contact over the notch. And here is the contact on the medial side. Here is the contact on the medial side. Here is the contact over the notch. On the patella, the contact is on the odd facet. Here is the contact on the odd facet. Here is the contact on the odd facet. Here is the contact, and here is the contact. So our femoral, our contact analysis and Yildirim et al. Contact analysis are in harmony. They are in agreement with each other. If you look at the tibiofemoral contact, again, you go from 90, 120, 135, and 158, and you can see that the contact, these are medial views and lateral views. If you look at specific views on the femur, at 100 tibiofemoral contact, On the femur, it is superior and posterior. On the tibia, there is a contact on the medial side and the lateral side. The lateral side, it is close to the posterior edge. On the medial side, it is appears to be on the posterior edge and in the intercondylar eminence. Now, how these results compare to others? Here is again one-to-one comparison between our results and Yildirim et al. Results. And this is the medial side on the femur, his results, and this is the medial side on the femur. This is the medial side on the tibia, this is the medial side on the tibia. Lateral side on the tibia, lateral side on the tibia. And you can see that we are predicting a contact here, which is the contact for the posterior impingement. And we are predicting a contact here, which she does, which is a contact over the tibial eminence. So what is the takeaway message? Well, the takeaway message is, as far as the patellofemoral contact, our studies have shown that the contact location shifts distally along the femoral groove. In deep knee flexion, contact is out of the patellar groove. In deep knee flexion, contact occurs on the odd facet. And that the contact area, in this method also, we calculated the contact areas. And we found that they decrease past 130-degree flexion, as again reported by Nagawa et al. On the tibiofemoral contact, the contact is asymmetric at large flexion angle. There is an impingement of the posterior edge of the tibia against the posterior femoral cortex. These take-away message were documented over several studies we have conducted, and they are in agreement with the studies that published by Walker et al. Group. So what is the challenge in deep knee flexion? And the challenge is still we don't understand what is the role of the menisci and the role of the different ligaments in deep knee flexion. We have shown that the PCL is tight in deep knee flexion. I did not report that. Other studies have also reported that the PCL is tight at deep knee flexion. What about the menisci? Again, there are studies, we have not reported that because we did not study the menisci. There are other studies who have reported that the menisci is squeezed posteriorly. Well, even if we understand all of this, there is a challenge with the total knee replacement designs. Because in a TQR, the ACL is gone. Anterior cruciate ligament is gone. There are some replacements, few replacements that I'm aware of, that are ACL preservative. They preserve the ACL. But most of the total knee replacement, the ACL is gone. The menisci are gone. There is no meniscus. When you do a total knee replacement, you remove the meniscus. Now, the PCL, there are total knee replacement, there are posterior cruciate ligament sacrificing, and they sacrifice the PCL, they cut it, they remove it, and there are some procedure where the PCL is kept. The MCL and LCL are preserved. So how these are tight, how these are tensioned. So how to come up with a design that mimic the normal knee function? That is the challenge. Because you have here, in fact, they are doing, and to my knowledge also, some of the TQR are called patient-specific total knee replacements. And what are those? If you look at them really, most of the advertised total knee replacement patient specifics are basically the specifics is the jigs for the procedure. They do a specific jigs for the patients using CAD and software, and then they do the surgery. What is the effect of a specific TQR on total knee replacement? This yet, on deep knee flexion, this yet has to be determined. You have mobile bearing versus fixed bearing. A mobile bearing is where the tibial insert is rotating. The fixed bearing is not. If you do have a fixed bearing, where do you put the anterior, where do you put the femoral component on the tibial insert? What is the slope of the tibial component? What is the internal external rotation of the tibial component when it is put on the tibial insert? The alignment, the mechanical alignment, and soft tissue balancing. All of this are factors in the surgical procedure. However, these factors affect the function of the total knee replacement. And that is a challenge in trying to come up with a design and a surgical procedure. I mean, the surgical procedure most of the time, except for very few studies, has been neglected. When we talk about a design, means you can come up with the best design, but in your surgical procedure, you may deviate. You may have different placements, which will affect the function of the replacements. I would like to acknowledge many of my graduate students who worked with me on this project over the years. Some of my colleagues in the medical campus, some of the postdoctoral fellows who worked with me on this project, and some of the medical residents who helped us in the experimental setup. This work was supported by 2 grants from the National Science Foundation. And if you visit Egypt and you go to the Egyptian or the old temples during the Pharaoh times, and you look at the walls, you will find pictures showing that deep knee flexion activity has been gone for a long, long time. And with this, I'd like to thank you for your attention.
Thank you very much for your interesting talk. Is there any question?
Any questions or comments?
All right. Apologize for the off protocol. How many cadaver knee joints did you actually measure in your setup?
In my experimental setup, we did 2 cadavers.
Okay.
2 cadavers.
So did you do?
And that is why we don't publish the data yet, because we need to do at least 4 or 5.
Okay. Thank you.
Thank you. If you think about the, if you think about the knee motion in daily life, till the horizontal position of the femur on tibia, our body gravity pulls the femur on tibia. After this, our body gravity pulls back the femur. And in this position, what are the resisting structures that resist to the pull of the femur?
Your question has, there are 2 activities. People need to differentiate there. As you go in squat, if you are doing a deep squat, right? If you are doing a deep squat, then you have the weight of the femur is active, going from up to down. You have the inertia, right? If you do kneeling, that is a quasi-static position. So during kneeling in deep knee flexion, I believe the side and calf contact provide a force that stabilizes the system. In deep knee flexion, doing kneeling, I don't know when the side and calf contact starts. That is why all of these models, and I had that in my presentation, but I removed it, all of these models are, all of these models, in fact, all of the published models are quasi-static. You need to have a dynamic model. In order to have a dynamic model, the model you must have differential equations, right? Because it is function of time. And you need to solve differential equations. We have done, and we have a study where we did a dynamic model for knee extension exercise. And that was very, very, very time consuming. And it was fundamental that I have to do that. So one of the things that need to be done to determine what is resisting this motion, what is resisting the weight of the femur, I know that what is resisting it in kneeling is the side calf contact, right? During deep knee flexion, there are many factors that I'm not able to identify them. When I'm talking deep knee flexion, because I'm not sure when the side and calf contact starts. You forget the side and calf contact, when you do that, you have the side is contacting the calf, right? So there is a force, kind of upward force, that work against or negate or stabilize or accumulate the weight of the field we are talking about. But that is innate. Now, when you go in deep reflection, squatting, I don't know these force terms. Okay. And also, the force of the quadriceps tendon, right? It tries then to stabilize the force of the weight of the femur going down.
Deep knee flexion, patellofemoral articulation won't work because the femur is pulling down.
You have seen the angle on the tibia. On the femur, yes, it goes down. That is correct. It goes down. It goes down. But it goes down. That is correct. I hope I answered some part of your question. In kneeling, it is the side calf contact.
Is there any question more? So thank you very much. So